Welcome back to the course Me22088 Vibration and Noise Control. Today we are diving into the main important topic forced vibration analysis of 2 degree of freedom systems. We will be building upon our understanding of single degree of freedom systems and exploring the complexity that arises when we have multiple masses and springs interactions. As you can see in this diagram, we have a classic representation of a 2 degree of freedom system. We have two masses, each denoted by m, and three springs, each with a stiffness k. The displacement of the masses are represented by x1 of t, x2 of t, indicating that they are functions of time. This setup allows us to analyze how vibrations propagate through the system and how external force can influence the motion of each mass. I am Dr. Sindhamarikanan, Associate Professor in the Department of Mechanical Engineering at SVSB. I will be guiding you through this topic and helping you understand the key concepts involved. Today, the first problem we are going to see is to how to determine the natural frequencies of a given car. Understanding these frequencies is crucial in vehicle design to avoid resonance and to ensure a smooth ride. Let's consider a simplified model of a car with the following conditions. The total mass of the car 300 kg, the wheelbase, which is distance between the front and rear axle, is 3 meters. Center of gravity is located at 1.5 meter from the front axle. The radius of gyration is 1 meter. Front and rear springs have a spring constants of 70 into 10 power 3 Newton per meter each. We will assume that the spring constants and distances from the axles are equal on both the sides. To find the natural frequencies, we first need to establish the equations of motion for the given system, that is, here it is car. This equation describes how the car vertical displacement x and angular displacement theta will change over a period of time. Using Newton's Huygens law, we can derive these equations. Initially, it is also given that since stiffness of the first front spring and rear springs are equal, K1 is equal to K2, and also we assume that L1 equal to L2. Therefore, let me derive the equations, that is, using the Newton's second law, it is mx double dot plus k1 plus k2x is equal to 0. And similarly, further if we simplify it, I theta double dot minus k2 kl square plus k1 l2 square is equal to 0. Now we assume the solutions. Since k1 equal to k2 L2, then these equations will be simplified simpler terms. Since this is equal, this will get cancelled, this is get cancelled. So the first equation is now uncoupled. What is coupled equation? Yes, in the previous video we seen it. That is, in the same equation we are having the x term, that is translational effect as well as rotational effect. Since now k1 L1 equal to k2 L2, this theta is get cancelled in the first equation, then x is get cancelled in the second equation. That is, we are getting an uncoupled equation now. It is now slowly, first equation is now slowly depends upon displacement only. Similarly, the second equation was changed into theta only. There is no x term in this. Now we can able to assume a solution for both these equations. That is, it is going to be x equal to a sin omega t, theta equal to pi sin omega t. You know very well that if I am differentiating x with respect to time, I will get velocity. Once again, if I am differentiating with respect to time of velocity, then I will get acceleration. Through that, I am getting that x double dot equal to minus omega square a sin omega t. What is this a sin omega t? That is x. So I can write it that x double dot equal to minus omega square of x itself. Similarly, theta double dot equal to minus omega square of theta itself. Now we can substitute in this here. Okay, that is in the our main equations. So the main equations will become as we can see that we are going to substitute this x double dot and theta double dot in our equations 3 and 4. When it is going to be substitute, we will get the values that here x double dot is equal to minus omega square of, this can be changed into a itself, otherwise or x also, so that is become as omega square a. Similarly, x is converted into a. So what will happen? Omega square equal to k1 by k2 divided by m. A will get cancelled here. So since k1 is equal to k2, this is 2k by m. So what is this next? Omega 1 is become as square root of 2k by m. Now we go to the next equation. In that, once again we are substituting, that is we are going to substitute here theta double dot equal to minus omega square of theta itself. What is that? Because this is theta equal to pi sin omega t, no? So omega pi sin omega t already is there. So minus omega square. What is pi sin omega t? It is theta. So theta double dot equal to minus omega square theta. That we are substituting here. Instead of theta double dot, we are substituting minus omega square theta. So minus omega square theta I plus 2k1 L1 square pi. You can even write it as theta or pi. What will happen means this pi will get cancelled. So at last we will get omega square equal to root of 2k L divided by pi. So we know that what is going to be the given mass of the car: 300 kg, wheelbase 3 meter, and center of gravity 1.5 meter, radius of gyration is 1 meter. Spring constant, that is K, is given as 70 into 10 power 3. Now in this omega 1 we can substitute K, that is 70 into 10 power 3, and mass of the car 300. If you substitute it, we will get the solution 21.6 radians per second. That is the first natural frequency. Similarly, we can be able to take the second natural frequency and substitute the moment of inertia. What is moment of inertia? It is nothing but mass of the car into radius of gyration. Radius of gyration is given as 1 meter. So mass is given as 300. So 300 into 1 square, you will get eventually 300 kg per meter square. Substituting this I value, already K stiffness value we know, that is 70 into 10 power 3 Newton meter. L1 we know that it is given that it is 1.5. Center of gravity is 1.5 meters from the front axle. If you substitute all these things put together here, we can able to calculate the omega 2, that is the second natural frequency of the system, otherwise second resonance set of the system, that is equal to 32.4 radians per second. So by solving this, we are coming to a very important note that this is we solved this car system as a 2 degree of freedom system. For the given 2 degree of freedom system, the car has two natural frequencies, that is one is 21.6 radians per second associated with vertical motion. The another frequency is 32.4 radians per second associated with rotational motion. This frequencies represents the rate at which car will naturally oscillate if it is disturbed. By understanding and controlling these frequencies, engineers can design vehicles that provide a comfortable and safe ride. It is very important, see, to note that what kind of problem we solve. It is nothing but we taken a multiple masses system and springs of also multiple springs subjected to a external harmonic force. Then what will happen? The response is going to be depends upon the system parameters like masses, spring constants. So we calculated the resonance frequencies. So resonance frequency is going to be very, very important. Why it is very important? Because there are multi-mass system. In this case, multi-mass means here it is 2 degree of freedom system. So two masses are kept. So two mass system has two natural frequencies, each associated with a specific mode of vibration. So we calculated the natural frequency by solving the equations of motions for the given system. So you keep it in mind. This is the way we have to calculate the natural frequency for any given application by simplifying the equations of motions. So we can able to design and develop any kind of systems such a way that it will be avoid resonance when it is excited by the external forces. Let's we see the next problem. That is, we are going to tackle another interesting problem involving natural frequencies. Imagine it is an electric train composed of two cars, each with a mass of 2000 kg. These cars are connected by couplings, which can be modeled as springs with a stiffness of 40 into 10 power 6 Newton meter. Our goal is to determine the natural frequency of this coupled system. To analyze the system, we start by writing the equation of motion using Newton's second law. Let's denote the displacement of the first car as x1 and the displacement of the second car as x2. The equation of motion is mx double dot equal to k, that is the stiffness which is there in between both the masses, will have the influence of both the displacement, that is x2 minus x1. In the similar fashion, you can also write for the mass 2, it is mx2 double dot equal to kx1 minus x2. This two equation describes how the acceleration of each car is related to spring force between them. Next, let me assume the motion of each car in sinusoidal form. So it can be represented as x1 equal to a1 sin omega t. And similarly for the second car, it is going to be x2 equal to a2 sin omega t. Here, a1 and a2 are the amplitude of the oscillations and omega is the natural frequency we want to find. Substituting these assumed solutions into the equations of motions, then what will happen? We have to see. For that purpose, we now differentiate x1 twice. That is, x1 if it is first differentiated, it is velocity. Second time, if it is differentiated, it is acceleration. Then what we will get? It is once again the same concept x1 double dot equal to minus omega square a. Similarly, the next thing. So let me solve it. We substitute this minus omega square a. Otherwise, it can also be represented as x1. Already we seen this. So we can able to represent this also as x1. So if it is substituted minus omega square x1 here and take commonly x1 on one side, left hand side as well as x2. So this x1 is taken commonly from this equation. After substituting this minus omega square x1 here. So we will get the equation in terms of x1 and x2. In the similar way, you also substitute this in this equation. We will get the second equation. So the second equation is kx1 minus x2 into k minus m omega square equal to 0. So what we have to do, we can able to solve this equation. When we are going to solve this equation, okay, what we are so if it is going to be solved, Here you can see that from these equations, if I am taking x1 by x2, it is k minus omega square by k. Similarly, from the second equation, you can write that it is x1 by x2 will become as k divided by k minus m omega square. So now we are having this both are equal. So we can equate this and this. That is k minus m omega square by k equal to k by k minus m omega square. Let me put everything on one side. From the previous slide, we know that is ratio of the amplitude is k minus omega square by k equal to k divided by k minus m omega square. Setting these two expressions equal to each other, we can able to get this is cos multiplied and we are getting k square equal to k minus m omega square, the whole square equal to 0. So solving this equation once again for omega, we find that these are the steps. First, initially we expand it, that is a minus b the whole square. So a square plus b square minus 2ab. We expand this and simplifying this. So what will happen? This k square will get cancelled. The next step. So this is get cancelled. So here you can equate this on one side. Then what will happen? Since this term is not equal to 0, so what will happen? Omega is 0. Next, you can able to write this one also. That is omega square equal to root of 2k by m. So in now, just now, we completed the calculation of natural frequency. That is, we solved this Carr-Bogie system and we got that natural frequency for this 2 degree of freedom system that we given in the problem. That is omega 1 is 0, omega 2 equal to root of 2k by m. Is it you remember what kind of system it is now? It's a semi-definite system because if the any system is going to be have a natural frequency 0, then it will be called as semi-definite system. So now let me substitute what is given in the problem. That is, we have to solve it and get the numerical value of the natural frequency. So what we do, we can able to plug in the given values. We have omega equal to root of k. Stiffness we have to substitute. Mass we have to substitute. That is mass is 2000 kg. So if we substitute, we are getting that it is 200 radians per second. Therefore, the natural frequency of the coupled train system is 200 radians per second. In summary, by applying Newton's second law and assuming sinusoidal motion, we were able to determine natural frequency of the coupled train. This problem illustrates how the concepts of equations of motion and natural frequencies can be used to analyze and understand the behavior of mechanical systems. Remember that the natural frequency is an inherent property of the system and is determined by its mass as well as stiffness. Thank you. Let us see you in the next video.